Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC1004. This is lesson 6. Lecture 6. Let's move on to our lecture. So this is your attendance. Please scan that as usual. Now let's recap on what we have done very quickly. So this is the thermochemical equation that we have seen before, and assuming that each of the components is actually an ideal gas. So you have PV is equals to nRT. That leads to the relationship between delta H and delta U, in which delta H is equal to delta U plus delta nRT. And delta N here is symbolizes the number of moles, the amount of moles for the products minus that of the reactants. And if any of the products or reactant is not a gas, it's ignored in the delta N. So we also saw the relationship between delta H, delta U, and Cp and Cv. So please refer back to the previous lecture notes and make sure that you're able to derive that relationship, how we actually arrive from here to here. Right, that's a good exercise for you. Now, what have we learned so far? Well, we have learned on this first law of thermodynamics, right? We discussed on the delta U being equal to work and heat, and the first law also identified the allowed changes. However, it doesn't actually tell you the information on the direction of the change, whether it's actually spontaneous or not. For that, we need another physical entity to actually quantify that. And that leads us to the second law of thermodynamics, which introduces a new state function, which is called entropy. Now, for many of you, you will associate entropy with disorder, the measure of randomness. Now, there is another opinion saying that this, is not quite accurate to actually quantify entropy as a disorder, because really entropy is a measurable quantity, and disorder is really a matter of opinion. A much accurate definition of entropy is really a measure of the amount of energy which is not available to do work. But I guess the word randomness or disorder is being used because it's easier for us to actually visualize what entropy is. So although there's a misconception or different opinion, so you get the idea what entropy is. So Clausius was convinced that there is a relationship between this, the fact that you have this energy not being translated to work is related to the heat delivered and the temperature at which it is delivered, right? And so this entropy came about. And entropy is a state function as well, in which it's not path dependent, so you only look at the S final and the S initial. So as I've said before, entropy is used to determine the energy not available for work in the thermodynamic processes. So during this work, you can't have this maximum amount of work, you can't have this 100% work. So where does the rest actually go? So entropy accumulates in the system, which then dissipates in the form of waste heat. So entropy really is a measure of tendency of a process to proceed in a particular direction. In other words, you want to know whether it's entropically favored. As you can see here, this mouth-watering lemonade here, the ice in the glass of lemonade will melt because as heat energy always flows spontaneously from surrounding into the glass, which has lower temperature. So hence you have this increase in entropy due to the disaggregation of the water molecules in ice. Right, another example to visualize this is is to see that the increment in entropy from A to C. First, you have a gas in a container separated from a vacuum by a partition. If you remove this partition, the gas will expand and will fill up the whole container. So you have higher entropy in this C here. So in nature, there are many spontaneous processes which are irreversible. So when you have a heated object placed in a contact with cold object, it's clear that it's spontaneous for the heat to flow from the hot object to the cold object until equilibrium is reached. And it's never the other way around. And when a gas cylinder is open, gas from high pressure will flow into the low pressure region, and it's never otherwise. So a thermodynamic system changes spontaneously until an equilibrium condition is reached. So, as I say, this second law introduces this entropy, and entropy lets us identify the spontaneous changes that can occur among those permissible changes. And really, the entropy of an isolated system increases in the course of spontaneous change. That means that if you talk about the delta S total, which is the surrounding plus system, is always increasing for an irreversible process. So you have irreversible process like free expansion, and you have the cooling of temperature. That is always accompanied by increases in the entropy. So reversible process doesn't generate entropy. There's no net entropy for reversible process. So really you have that for the irreversible process, the S final is always larger than that of the S initial. But if it's a reversible process, the final and the initial will always be the same. So hence you don't have this net entropy gain. So the thermodynamics definition, in the definition equation wise, the delta S is defined as Q reversible over T. So the entropy change of a substance is equal to the energy transferred as heat to it reversibly divided by the temperature at which the temperature takes place. So in other words, so you have this Q ref is equals to over T. So by making this transfer reversible, so there is actually no hot spots generated in the object, and so that will actually disperse spontaneously, so that will then add to the entropy, so that's why it's actually Q reversible. Alright, so now there is also another way to actually define change in entropy in specific processes. For example, at phase transition. Phase transition, for example, from liquid to solid, which is freezing, from liquid to gas boiling, accompanied by change of entropy. Alright, and at the phase transition, the system is in equilibrium. Okay, so the energy is therefore transferred reversibly and isothermally between the system and the surroundings heat. So if you're talking about constant pressure, so remember that Q is equals to H delta H. So hence the change in entropy of the system is delta S equals to delta H transition over T. Now, so you can have the system being freezing or condensing. Heat is liberated to the surrounding and there is a loss of heat. So you have delta H transition being negative. So the entropy change is negative for the system. And when it vaporizes or melt, there's heat added. So you have delta H larger than 0, positive. So it becomes more disordered. Okay, as how we will visualize it. So the entropy of fusion will always be less than the entropy for vaporization because the gases are more disordered than liquids, and liquids are more disordered than solids. Okay, let's look at an example how we do this. Say the latent heat of ice is given as 6.02 kilojoules per mole and its melting point is 100 degrees Celsius, or in Kelvin 273. Calculate the change in entropy when ice melt and calculate the entropy of vaporization if the latent heat is 40.6. So this is simple. You have the delta S fusion over delta H transition over T. So this is the delta H transition for the fusion, and this is the temperature at that point of transition, so that gives you 22. Delta S vaporization, so this value will be given, all right, these two values. And this is a boiling point, which is 100, which is equivalent to 373. That gives you 109. That looks right because we expect that the delta S for vaporization to be much larger than the fusion, for fusion, due to the large increase in disorder during vaporization compared to melting. Right. Now, we have seen before in previous lectures that for an isothermal expansion, all right, the work done is equals to minus nRT ln Vf over Vi. And for an ideal gas that expands isothermally, the delta U is going to be 0. Hence, Q is equals to minus W. Now that leads to delta S equals to Q. That leads to this, what we express, delta S equals to Q over T. That leads to delta S equals to nR ln Vf over Vi. So plugging this into this equation. So from this we can see that when there is an expansion, right, so Vf is going to be much larger. So you see that delta S is positive. When the gas is compressed, Vf is much smaller than Vi. That leads to delta S being negative. So let's plug that into an example. Calculate the entropy when 1 mole of gas doubles its volume. Alright, so you have 1 mole times the gas constant times ln 2. Why ln 2? Because it doubles, so this must be 2, this is 1, so that means ln 2. So that gives you 5.76 joules per Kelvin for delta S. That's very simple. Alright, now let's find the relationship between the first and second law of thermodynamics. Alright, so remember that we have this, the first law being delta U is equals to Q minus P delta V for reversible process. So you have that. Okay, the second law talks about that, alright, and you can rewrite that to Q ref T ds. Alright, so if you combine equation 8 and 9, you get delta U equals to T ds minus P dV. So now let's try to define this when you have a process for processes at constant volume. So let's divide equation 10, which we derived just now, by dt and hold V constant, because we're holding one variable constant. So you have this partial derivative of so you have this del U over del T over V equals to T del S over del T V. So really, so you're just taking that into this, okay? And this is just to remind you that we have seen before that du over dt is equals to cv. Alright, so then that leads to cv. So if you rewrite that, what you get really is the delta s over del t is equals to cv over t. Alright, so equation 11 provides a way to calculate entropy changes for process at constant volume. So if you set that up for integration, so you have ds over cv over dt. Alright, so now you can take the integration of both. So then you have that what do you call cv over t, and cv is a constant, so you can take it out. That becomes ln t2 over ti. So delta s is equals to cv ln t over 2 over ti, sorry, t2 over ti, t final over t initial, assuming cv is constant. Right, and at constant pressure, alright, so we saw from equation 10 du is equals to t ds minus p dv. Alright, and so we have this dh equals to t ds plus v dp. Divide that by dt and keeping p constant, so you have here the partial derivation here. Alright, so then that leads you to delta sp equals to cp over t, that gives you dt. So what you have here finally is delta s at constant pressure is equals to cp ln the final temperature over the initial temperature. So now you see the relationship between that, how you relate the first law and the second law, that leads you to this expression at constant pressure and at constant volume. So an example of this of using this expression, so this is not example 1, this is example 3 actually. What is the entropy change when 1 mole of aluminum is heated from 300 Kelvin to 500 Kelvin at constant pressure? And this constant pressure is given as such. Don't be intimidated by this expression. So all you have to do is just apply the integration. So delta sp over is actually the integration of this. So you have this cp over dt, and so you have 20.6 over t, alright, dt plus 12.38 over dt. So you have that 20.67 over 500 ln 500 over 300 plus this expression, okay, times that of this. So that gives you 13.04 joules per Kelvin. Alright, so work out this exercise and the other two examples so that you can understand what we have covered for this lecture. Alright, so that's all for this part of the lecture. So I'll see you again in the next lecture. Alright, okay, bye for now. Thank you. Assalamualaikum.